Okay, everyone, welcome to Chem 1331. As soon as everyone gets settled in, we'll get started. And I'm going to start this semester the same way I start everyone, which is to quickly admire how full the classroom is, because it'll never be like this again. But I appreciate you all coming today, and hopefully you'll stay around for more than today. So today we're going to start by going over some highlights from the syllabus, as well as some unsolicited advice that I have about how to do well in this course, which I hope some of you will listen to as well. So let's get into it. All right, so in case you didn't read the syllabus, here's the highlights. So the textbook, as some of you have been asking about, is Zoomdale and Zoomdale. It's Adam's first approach in particular. They might have written another conventional textbook, so I'll make sure you're aware of that. The bookstore sells like a loose leaf version. It's called the US or UH Custom Edition. There's nothing special about it except that it's a little bit cheaper than you can often find from other vendors. And it is loose leaf, I believe, so you have to bind it yourself. But anyway, if you get it at the bookstore, but if you find it online somewhere else cheaper, or you inherit one from someone else, any Adam's First Approach by Zoomdale and Zoomdale Second Edition will match up well with what we cover in class. So second edition especially. First edition is okay. It's just going to be a little bit different order or page numbers and things if I ever refer to that. Another frequently asked question is about the access code. You don't need it for this course. There are some additional features that it will give you access to, as the name access code implies. But we're not going to use any of them for required assignments, or I'm not going to really refer to any of that in my own teaching. But if you have the access code, you might find it helpful, but you don't need to get it. We'll have plenty of other resources for you provided through Blackboard. Another thing that's good to get used to right off the bat is using a non-programmable calculator. So I know in a lot of math courses you use these fancy graphing calculators. We don't allow those in our tests, so you might as well do all of your homework assignments with that calculator and get used to it. There's nothing more frustrating than missing a question because you don't know how to use the calculator properly. So get some practice, make sure you have one available. So the grading in this course, as you are likely aware, is not the most user-friendly, but it is what it is. So we have 3 midterm exams. They're going to be spaced pretty evenly, about 1 month apart. So the first one will be February 18th and 20th, and then about 1 month after that for each other one. So those are worth 20 points each, so that's about 60% of your grade. Your final exam is 34, so that's another 34%. And the homework, the weekly homework assignments are going to be 6 points total. So they're going to be averaged together at the end of the semester. And typically we drop 2 homework assignments. I don't know if that's on the syllabus, but that's typically how we do it. Drop your 2 lowest. But anyway, and then as I'll talk about more later, we have bonus points. This is actually a mistake. I just changed some things, so we're not going to do in-class quizzes this time, so I forgot to update the notes. I'll give you some more information about the bonus a little bit later. So that's how we calculate your grade. It's mostly exams, as you can see. We don't drop any exams either, so all those will count. And then the grading scale is a little bit friendlier than the typical UH scale, the standard UH scale. So we have an A is 90 and above, A minus 85 to 89, and so on. So we do use the plus minus scale all the way down. So to get a grade, to get a passing grade, you need a 50 or above. Many majors require you to get a C minus to actually pass and count it towards your major. So in that case, you would need a 60 or above. So that's kind of the minimum, but obviously we're all going to shoot higher for that. But this is the scale. And another common question that comes up, especially at the end of the semester, is do we curve? This is the curve right here. We don't do anything. We don't make any adjustments to that scale. So you're not competing with each other. That's the nice thing about it. It doesn't matter how many of you get a certain grade. If everyone in this room gets a 90 or above, you all get A's. We're not going to compete you against each other, and we're also not going to adjust the scale in either direction. So you're competing just against the grading scale, not against each other. All right, so that's kind of the basics. Now, the weekly sort of tasks that you're going to have is homework assignments, and I'm going to talk about the importance of these more later on. But essentially how they work is they're going to be done on Blackboard. So if you have not used Blackboard yet for any of your other courses, make sure you become familiar with it, because you will use it every week here. And typically each chapter in the textbook has 1 to 2 homework assignments associated with it. So each homework assignment will cover roughly the last 1 to 2 weeks of material that we've covered in class, and I will try my best to stay ahead of the homework. Typically I'm able to do that as long as I don't have any unexpected cancellations for snow or ice or whatever. So we'll be able to keep ahead of the homework assignments. So it'll be stuff that we've already seen and already covered. And as I said, there's one each week, so roughly about 12 or 13 assignments. It depends on how exactly the semester aligns itself, whether that number is 12 or 13, but it's going to be one per week more or less. The first one is not due this week, though, so the first one is not due until the 27th. If you go into Blackboard, all of the deadlines for the homework assignment are listed in the homework near the homework folder. So if you're ever curious or confused about when the homework assignments are due, they're right in there in Blackboard. They're also on the syllabus, which if you have time to read, I encourage you to. All right, and then there's, as I said, 12 to 13 assignments. We typically drop the two lowest from your total score, so you have a little bit of flexibility if you miss one or completely bomb one out. And as I already mentioned, it's 6% of your grade. Now, each homework assignment is 12 questions, and there's a 48-minute time limit. So it's not too fast. It's actually a little bit slower than the exam time limit, so you have plenty of time to work through them. And we give you 4 attempts maximum per week. Now, one thing I don't have written here is that in terms of your base homework score, only the highest one counts for that week. So if you do 4 attempts and you get a 9, 10, 11, 12 out of 12, the score that goes in your grade book is the 12 out of 12. We don't count all of them. Now that said, as we're going to talk about a little bit more in the next couple slides, and I'll give you some more details as we work it out at the beginning of this term, we are this semester going to have some bonus points that are tied to how many homework attempts you do. So even though you really only have to do 1 homework attempt a week to get a perfect homework score, because we only count your highest one, there will be incentives this semester for doing additional attempts beyond that 1 minimum requirement, which, as I'll show you, is a very important determinant for how well you can do in this course. All right, so that'll all work itself out, but essentially, in terms of the homework grade, you can do it up to 4 times. We count your highest one. So here's the timing of it is Sunday to Sunday. So the new homework assignment will open up Sunday at 12 a.m. I think for this first one, it actually opened up this morning at 12 a.m. because this was the beginning of the semester. But typically, a homework assignment will become available Sunday at midnight, and then it will be due the following Sunday at 11:59 p.m. So you essentially have exactly 1 week to do it. Now, you have to be a little bit careful because the habit of many Chem 1331 students, despite my discouragement to the contrary, is to do the homework assignment on Sunday night and not to do it until Sunday night, which I recommend against, but many of you will do. And if that's the situation, if you're going to wait that long to do it, keep in mind on Sunday there's going to be 2 assignments available. There's going to be the new one that just opened up and the one that's due at night. And just make sure you do the correct one. So check the due dates, check the syllabus if you're not sure, to make sure you're doing the correct assignment. They are numbered, so the smaller number is due before the larger number, Chapter 2 before Chapter 3, and so on. But occasionally there's some confusion there, and it's not easy for me to go back and fix that if you make that mistake. So the best thing is just make sure you do the correct assignment if you do it on Sunday, when you'll have 2 to choose from. One that's not due until the next week, one that's due that night. Now, the other thing that we have is what are called practice homework assignments, and these are the exact same group of questions, the exact same question bank as the regular homework assignments. They open up after the homework is due, and it allows you to do it, I think, 3 more times. We kind of change the number of attempts once in a while, but I think it's still 3 additional attempts that you get on the practice homework assignments. Those don't count for anything. It's just for you to review. And a lot of people save those, or at least some of those attempts, for exam time. So, when they're spending that last couple days or so reviewing for the exam, they'll go back and do old homework problems, because most of our exam questions are very similar to homework questions, so the more of those you do, the better prepared you're going to be. All right, so we have practice homeworks, which are another nice resource to use, but they don't affect your grade at all whether or not you do them. All right, so here's some information about the exams, which you'll all come to know and love as we come and do them. So we take the exams in CASA, which is probably everybody's least favorite place on campus, and we'll keep you posted on which CASA location we use. We sometimes use Garrison, sometimes the business building one. It's up to them to assign it to us, so I'll make sure we're clear about that. When you sign up, you can see in CASA. The exam sign up is about 2 weeks before. We'll cross that bridge when we come to it, but you will need to sign up for a time to go take the exam, and it's usually a span of 3 days that we'll have each exam open for, and you can take it any time those 3 days it's available. The midterm exams are 20 points and they're 20 questions, so we keep it nice and simple. Each question is worth 1 point, 1% of your grade, and there's a 75-minute time limit. So as you can see, it's a little bit faster than the homework. The homework is 4 minutes per question. The exams are 3.75 minutes per question, so very similar but a little bit faster. The final exam is 34 questions and has a 100-minute time limit, so a little bit quicker pace on that one too, but should be stuff that we've already seen before. You'll get used to the types of questions we have from the homework assignments. As I said, they're very similar in difficulty, in scope, not necessarily in the exact type of problem, but if you can do the homework problems, you should be pretty confident you can do most of the exam problems, or all the exam problems really. And it's going to be multiple choice and answers that you have to type in, short answers like numbers or one-word answers, things that a Blackboard grading system can easily handle, because we don't do any hand grading in this course. As I said, you're only allowed to use a scientific calculator. You are expected to bring that with you. That's not provided, but it has to be scientific and not graphing. And we will provide you with a periodic table and a list of constants. So that is posted in Blackboard in one of the folders. I think Downloads folders is called. So if you go to the Downloads folder on Blackboard, it has this periodic table in there that we're going to use on all the exams. So it's also good to use that for homework assignments, get familiar with it, to know how it's a periodic table, so they're all the same basically, but ours doesn't have the atomic names on it, so you want to be familiar with that, and also the list of constants that's at the bottom, stuff that'll come up more later on in the semester. All right, and with the exams as well, my intention is to stay well ahead of the exam material, so that we'll finish it a week or two before the exam starts, and you'll never have to have brand new material on the exam. When you take the exam in CASA on Blackboard, you're going to get your score right away, so as soon as you click submit, you'll, unless you avert your eyes, you'll be able to know what your score was. And however, you won't know which questions you got right and wrong or anything until afterwards. So once everyone finishes the exam, we release the results and you can review them. And if you think there is a problem, an issue with one of the questions on the test, we do accept regrade requests up to 1 week after. Very rarely do we change people's exam scores, but it's not unheard of. So if you think there's something wrong, we're happy to address that. But you need to do that within 1 week of the exam. I don't want to be assigning final grades and having people requesting that I look at their old scores and see if they can give me one more point. No, this is too much. So it has to be 1 week after the exam, or it's too late. Okay, so that's the stuff about exams. All right, so this is the slide that changed. If you were an overachiever who downloaded the notes before last Friday, it's going to look a little bit different, but we changed our mind on how we're going to do bonus points this semester, and I'll give you the reasons a little bit more detail later on. So in the past, our bonus points, which they're up to 2 that you can earn, so the class is 100 points, you can get 2 additional as bonus, so in reality, the highest maximum grade in this class is 102 out of 100. But anyway, in the past, we tied it to class attendance. We would do unannounced quizzes, and typically the way I did it was, if you were here and did the quiz, you got half of the credit. If you got the question right, you got the full credit, and so on. And there's still benefits to coming to class, as I'll show you, but we've kind of figured out that really what the habits that the best students have are to do all 4 of those homework attempts every week, and to practice throughout the week, not just wait till Sunday night to do one and forget about it. So we are going to try to encourage you this semester to use those homework attempts to their fullest extent possible, and to do that, that's how we're going to calculate bonus points this year. And there's still some details that are, I'll reveal to you later on when we sort of work them out. This is a coordinated effort between myself and Professor Larson, who's teaching the other 2 sections, so we're going to try to make things the same for all the sections this year. And essentially, the bonus points are going to be tied to the number of successful homework attempts you complete. We have yet to define successful. The traditional definition in this course is an 8 out of 12 or higher. We're not sure if that's the standard we're going to use for the bonus calculation, but the point is we're going to want you to actually put effort into the attempts to count them. We're not going to just let you open up a homework assignment, click submit, and get a bonus point for that. That's not the point of this. So we want you to actually do 4 attempts and actually try on all 4 attempts to do most or all of the questions and to get as many right as possible. So it's going to be somewhat based on how much effort you put in attempts. Again, we're going to define that more carefully later on. But really, the reality is the more homework attempts you do, the better your bonus grade is going to be. So I think the way we're leaning towards doing this is we're going to take total number of homework attempts that you do. So I think if there's 12 homework assignments, there's going to be 48 maximum attempts. I think last semester there was 13 assignments or 52, so 4 per week, as we said, is the maximum. So if you did all 48 homework attempts and you cross whatever our threshold is for a successful attempt, whether it be 6 out of 12 or 8 out of 12, however you end up defining that. If you got that, you would get your full 2 bonus points. If you did 24 homework attempts that were above the threshold, you would get 1 bonus point. So basically the maximum is 2, and then whatever percentage of those number of attempts you end up completing is going to determine how many bonus points you get. And as I'll show you in a little bit, there is a lot of data that we have to back up the idea that the more homework attempts you do, the better off you're going to be. And so we want to encourage that and give you an incentive to do that beyond just the inherent benefit of learning the material better. All right. And then finally, some specific information about this section. So my office is just right over there. So we're here right now in this little circular thing. You just have to go under the pedestrian bridge, the little overhang, or whatever we call it, to get to SERC, S-E-R-C. And then I'm on the 5th floor of that building. The elevators break roughly once a week, so hopefully they're working when you come to see me. All right, so the scheduled office hours are going to be every day 11 to 12, so 11 a.m. to 12 p.m. That's just, now keep in mind when I say office hours, those are the times when I will prioritize being in my office and being available. There will be rare cancellations that I'll let you know about ahead of time, either in class or on Blackboard. For example, this Friday I won't be there, but just about every day at 11 a.m. to 12 p.m. I will be, camped out in my office, and those are the times I prefer you to come if you can, because that's kind of the time I set aside for that. That said, I'm in my office most of the time every day, so if you need to come another time or can't come during those times, feel free to email me to schedule an appointment. If you walk in and I'm there, I'll be happy to talk to you. I just can't guarantee I'll always be there. But really, I'll try to be as flexible as possible given how many of you there are, and I do want to be able to help as many of you as possible that are willing to come in for that. Email is the best way to contact me, so I have it listed here. It's probably on Blackboard too. So that's the best way to get a hold of me reliably. If I'm in my office, I will likely answer my phone if I'm not too busy with other things going on. You can call that as well, but email is the best way. So please, you use office hours to your advantage. As I'll get into the more discussion on the homework assignments, a lot of the students that do well in this course, not only are they doing the homework assignments every week and doing all 4 attempts, but they will come see me pretty regularly with the questions they don't understand. And just really trying to learn everything very gradually, not waiting until the week of the test to come see me for the first time, which is not usually a very winning strategy. All right, and then the last thing I think I want to point out about this course is the YouTube channel that I have. Some of you might have seen this before or heard about it. So essentially, I'm going to post a lot of things there on a regular basis. There's already a lot of archive material that you can check out if you're curious what it's like. But each lecture will be recorded. That's what this little recording bar in the top right is telling us that's happening right now. And that'll post after class, probably in the evening sometime if I'm not too busy that evening. And then in addition to the lecture videos, there's homework reviews that are going to be done every week after the homework assignments are due. So that's just me by myself in my office. It's not really a session for you guys to come to, but I will record a video that goes over the questions on the homework that we had the most difficulty with. So one of the nice things about doing it on Blackboard is I get really nice statistics about which questions we did well on and which ones we did poorly on. So I'll pick a representative sample of questions that I think we struggle with and kind of go over them and review them and maybe catch up on some things that I might have missed when discussing it in class. Also, you're welcome to suggest problems to me. So if you want to, if there's a homework problem you had trouble with, just email me during the week. Hey, can you go over this on your homework review, and I'll include it. So that's another way that I can get material for that. Those are usually like maybe 30 minutes or so on average, so not real long, but just a quick highlight of some of the previous week's homework. Exam reviews are going to be held Friday afternoon before each exam. I'll have more details about those as they approach in terms of where they are. Usually they're 1 p.m. on Friday, as long as I can find a classroom. So those are open to the public, but they will also open to the public, but they will also be recorded and placed on YouTube in case you can't make it or you want to rewatch it afterwards. Now, a lot of students, you guys grew up in the digital smartphone age, unlike old guys like me. So YouTube's kind of one of your favorite resources, and that's fine. I hope you'll find it useful. But remember, it can't be the only thing you do. So all these things I'm talking about, coming to class and doing homework assignments, that's going to be important for you as opposed to just casually watching YouTube videos while you're doing 10 other things and socializing and all that stuff. So use these resources to your benefit, but don't think it can be really the only thing you do if you want to do well in this class. Now, to get more specifically in what does it take to do well in this class, I have a lot of statistics from last semester that kind of show you how the students did and which which types of habits are conducive to that success in the course. So first of all, I think in the notes I printed online I had this as a C minus. 64 is a low C on our scale. So the average grade last semester was a C. That's been pretty true for the last few times I've taught this course. That number doesn't seem to change a lot. Now I'm sure most of you would not be happy with the C, so we want to try to do better than that. And here's the distribution. It covers the whole range from not so well to getting solid A's. And again, so it's a difficult course. I might be old and sometimes out of touch, but I'm aware of the perception of this course as being difficult and one that a lot of students have trouble with. So I do want everyone to do as well as possible and really try to build the habits that you need to succeed. Because there's nothing that's stopping any of you from doing well. It's really just a matter of finding the resources that work for you, building the work habits that you need to succeed, and then also really getting off to a fast start from day one. So don't wait until 4 weeks down the road when our first exam is approaching to really get into gear. You got to start now, and then if you're able to do that, you'll really be able to stay on top of things. All right, so that's the grade distribution. Now let's look at the factors that affect people's grades. So the first one I want to talk about is attendance. So last spring when I taught this course, I did take attendance a few times through those bonus quizzes that we used to have. So it's not very many data points for attendance. I didn't do it every day, but I have 5 or so that are spread out throughout the semester. This last one I don't necessarily count as strongly because I announced the bonus quiz in advance that day to get people to show up for student evaluations. So the rest of these are unannounced quizzes, so it's just random attendance points throughout the semester. And as you can see, it started out pretty good, 78.5%, and then it kind of leveled off at about 70% attendance for the rest of them. So hopefully we can do a little bit better than that, although I'm not going to keep track this year. Now the question is, does coming to class affect your grade at all? So if any of you have any background in statistics, I just did a real rough plot here. So basically this is each course attendance percentage, and there's only really 5 possibilities. Either the student came 0 of the 5 times I took attendance, or 5 out of the 5 times, or some number in between. So those are just the 5 possibilities for the percentage of classes that they attended out of those 5 that I randomly sampled. And then this is the scatter of the different course grades. Now as you can see, there is a lot of scatter, so there's no guarantee that coming to class is going to mean that you're going to do really well in here. But there is a small positive correlation. R is 0.22, so anytime R, this is the correlation coefficient. Anytime it's a positive number, that means it is positively correlated. And so there is some effect of coming to class regularly on your course grade. So coming here is at least indicative of not necessarily a causational relationship, but at least is one of the habits that you'd want to try to build up as you're trying to do well in this course, is to come to class regularly. Now the one that matters even more is homework. So what I'm showing here on the left is, this is each homework assignment we had last semester. As I said, there was 13 last semester. And this is the average number of attempts per student. So as I said, each person could do up to 4 attempts, and generally with very little variation from week to week, the average student did about 2 attempts per week. So they're throwing away half of their possible homework attempts. And there's a pretty wide scatter there. There are a fair number of students that did 3 to 4 attempts every week, and then there's a lot of students that waited till Sunday night and did 1. So this is just the average that I'm reporting. But on average, two attempts per week, and as I said, we can do up to 4. So you really want to try to use all 4 of those, and that is important here. So here's the scatter plot for the number of homework attempts that each student did with their final grade on the y-axis. So this is every student in the course last semester. With again, on the y-axis is their final course grade numerically. On the x-axis is the number of homework attempts they did. Again, there's a lot of scatter, so it's not a real predictive measure, but there's still a R of 0.35, so a small to medium positive correlation indicating that the more homework attempts you do, the better your expected grade is in the course. So you can kind of see that, right? The people that are way down here on the y-axis, people that had the lowest grades in the class, tended to not do very many homework assignments, and then the people that did the maximum number of homework assignments up there tended to have grades that were well above the average. So to give you an idea of how significant this is, let's say you did 2 homework attempts a week. You were one of those average students that just did 2 per week, and then using this the equation for this line, y equals mx plus b, this best fit line, which is, again, a crude approximation of how this actually works, but a relatively instructive one. If you did the average number of homework assignments, your expected grade was the average grade in the course, 64%. That matches up pretty well. Now, if instead you had done 4 homework attempts per week, if you'd maxed out and done all 4 of them, your expected grade would be a 78%, which is a B. So it has a very big effect going from just doing 2 attempts a week for doing 4, at least on average. Now, as you can see, they're scattered here, so there's no guarantee that's going to be your outcome. Statistics don't predict individual outcomes, they just explain previous ones. But at the same time, there's a pretty clear demonstration here that if you do the maximum number of homework attempts, you're going to end up performing pretty well in this course, more likely than not. Now, to give you some more examples of how this works. So what I'm listing here on the left are some of the statistics. So I randomly selected the top 15 overachievers in last year's class. These are the 15 people that did the most attempts out of the whole class, which ranged between 49 to 52. So 52 is the absolute maximum. So there were about 5 students who did every single homework attempt allowed to them, and then there was 10 others that were pretty close to doing that, just missed maybe 2 or 3 the whole semester. So looking at how these students did, the students that did all 52 attempts, 1 of them got an A, 3 got A minuses, and 1 got a B. And you can see that if the students that missed just 1 attempt, both got B pluses. 50 attempts, the student got a C minus. 49, there's a mixture of grades ranging from A to C minus. So the point being, out of these 15 students, only 2 of them got below a B. We had, maybe it was 3, I can't count. 3, either a typo or an inability to count. But still, 12 out of those 15 students got B minuses or higher, which I think most of you would be fairly satisfied with in this course. So the point is, if you do a lot of homework assignments, and especially if you're trying hard on them, this data here doesn't really keep track of how hard they tried on those assignments or what scores they got or anything like that. It's just how many they actually did. And the students that did a lot of homework attempts, all 4 every week or very close to that, all got pretty good grades in this class. So I think the average grade out of these 15 students is probably like a B or maybe even a B minus at the worst, like a B or so. And so if the average grade for all of you guys was a B, I would be ecstatic. That'd be significantly better than we've been doing. And we do think, both Professor Larson and I agree on this, that the more time you spend on tasks throughout the week and doing those 4 homework attempts and spreading them out throughout the week and not waiting until the last minute, all of those things are going to help you do well, and I think the data is very supportive of that, so I hope that this will encourage many of you to put that effort in that you need. So we will have more details about how the bonus calculation is going to work, but it is going to be tied to your number of homework attempts. It may even be tied to when you do those homework attempts to encourage you to not just do them on Sunday. So we're going to work out those details and see how easy or difficult it is to implement. But really, if you come to me at the end of the semester and you say, well, I'm not happy with my grade, what could I have done differently? If I look at your homework assignments and you're not doing close to 4 every week, then that's immediately the first thing that I can notice that you probably could have really helped you out. All right, so that's the end of my motivational speech, which probably wasn't very motivational, but maybe to some of you it was. Now we have to start talking about chemistry, which I'm much more interested in talking about than motivational behaviors and things. So let's get into it. So we're going to start right at the beginning of Chapter 1 in our textbook. There is a review chapter that's good to look at on your own. It has some of the little mathematical things and units and conversions, stuff that I won't directly teach in very much detail that you're expected to know. So there is a chapter R in the beginning of your book, review chapter. Please look that over on your own. If there's anything that you're not familiar with, try to pick it up. But we're going to start with Chapter 1 as we go through today. Now, the first thing I want to cover, which you will likely also encounter in the chemistry lab whenever you take that, is the scientific method. Because what we're starting with in this course is a description of some of the early discoveries in chemistry. How did the field of chemistry come about? How did we really develop our knowledge to what it is today, or at least to get the basic fundamentals down that are so important for understanding all of the rest of chemistry? And that came through careful application of the scientific method. So the scientific method starts with an observation. An observation is something you sense or measure. And one thing that's helpful to be familiar with is that there are 2 types of observations. There are qualitative observations, and that's something where you kind of judge something, but there's not a specific number associated with it. So if I said the sky is blue, that is a qualitative observation. Blue is not a unit of measure. It's just a color, for example. Or if I said, this person is bigger than that person, I'm using a qualitative observation, but one that doesn't have any sort of numerical value. And then there's quantitative observations which have a number and a unit associated with them. So if instead of saying, this person is big, I said this person weighs 273 pounds, that's a quantitative description of that person. So observation is really where the scientific method starts. You notice something, whether it be something that you can just sort of judge intuitively or qualitatively, or whether it's something that you measure using a more sophisticated approach. And then from that observation, you develop a hypothesis. Now, a hypothesis is a possible explanation. It's not usually totally off the wall. It is based on some sort of preconceived knowledge that you have, or in the case of an observation, what you're sort of noticing from the observation. So it's not just a total wild guess, but it's a possible explanation for that observation. And it's usually based on flawed or limited information. So making one observation or even a series of observations is often not enough to really know what's going on. And your hypothesis is just a way of, well, maybe this is what's happening, or maybe this is an explanation for it, but you don't have enough information to really be conclusive about that. So the hypothesis, often people refer to a hypothesis as a guess. I think a guess kind of downplays the importance of the hypothesis. It really is based on information you already have that you've learned from other experiments you've done in the past, plus the current set of observations you have and what you think they're trying to tell you. But again, you might be wrong, and that's okay. Then the way that you want to know if your hypothesis is correct or not, and how to refine a hypothesis and really understand what's going on, is you design experiments. So these are designed to carefully test the hypothesis. And so usually the way this works is when you're designing experiments, you have your observation, your hypothesis, and you say, well, if I were to do this experiment, if my hypothesis is correct, this will be the outcome. If my hypothesis is incorrect, this will be the alternative outcome. So you see the outcome of your experiments and whether or not it matches the hypothesis you've written. So perhaps to give you, perhaps to give you an example of this, a kind of a silly one, but let's say, when Isaac Newton discovered gravity, how would he have used the scientific method to come up with the idea of gravity? So his observation, at least the one that you classically read about in folklore, that I don't know if this actually happened, is that an apple fell on his head. Poor guy, but he got through it. So the apple falls on his head. That's his observation. Oh, this apple just fell out of the tree. And then so he becomes wondering, well, what caused that to happen? So let's say he came up with a hypothesis, and his hypothesis was, well, I think the apple tree threw it at me. That's why the apple came down and fell on my head. Now, we all know that that's ridiculous, but again, based on that information, an apple falling on your head, maybe that's what you think happened. And then you go and you design experiments to test it. So you try, you drop an apple off of a building and, oh, shoot, it still falls on my head. Or you try a rock instead of an apple and, oh, it still falls on my head. So clearly the apple tree is not projecting the apples at you, so you have to refine your explanation and go and do more hypotheses until you figure out that, oh, there's actually a attractive force between the apple and the earth, and that's what's causing it to fall. So it's really just that's how the scientific method works. It's guess and check. You make a guess of what you think is happening, you design an experiment to test that, and you just go around and around and around until you're very certain of what you think is going on. And what comes out of all of this then, we have this whole scientific method that repeats itself over and over again. There are two things that come out. So one is a law, and we're going to talk today about some of the early laws of chemistry. And a law is just a description of what happens. So laws can be, again, sort of qualitative statements, or they can be equations, mathematical relationships that come out of doing a bunch of experiments. So in the case of gravity, the law would be something like, two objects with mass have a force of attraction between each other. That's sort of the qualitative statement of gravity. And then there's the equation, gravitational force is mass times g times acceleration, if I'm remembering my physics correctly, but I'm not a physicist, so don't quote me on that. But anyway, there's an equation also for gravity that would come out of doing all kinds of experiments and figuring out, how fast things fall and all that stuff. So there's laws are a combination of statements of fact and equations or mathematical relationship that describe those facts. We'll see a lot of that in this course. And then the other thing that's very important for science, these two kind of go together, is the theory, which is an explanation for why it happens. Now, the theory of gravity is a little bit more complicated and wasn't really worked out in full detail until much later. So a lot of times you'll have laws which exist for some period of time without a solid theory to support them, or sometimes the theory initially is wrong and has to be refined as more observations are made. But a way to think about a theory is that a theory is basically a hypothesis that has stood the test of time. So it's an explanation for a series of observations. Why do we see this? Why do we observe this? And it's one that has endured a number of rigorous experiments and has gone through the scientific method over and over again before it is widely accepted as being a true explanation. It can still be refined or changed in the future. Science is never 100% certain on anything, but a theory is more or less an explanation that works out very well for a set of observations and is believed to be true. So law is what happens, theory is why it happens. That's kind of the distinction between those. All right, so we have the scientific method is sort of the basis of all of science and chemistry in particular. And before we get into some of the specific examples of how the scientific method was used in chemistry, let's kind of break down what exactly we're talking about with chemistry. So I gave you a very stupid physics example to explain that, but we're going to be talking about chemistry in this course, and what are the types of things we're interested in when we talk about chemistry. So chemistry is the study of matter. Matter is anything that has mass. So really anything you would describe as stuff is matter. It's a lot of different types of matter, but we can break it down sort of systematically and talk about how do we classify matter in the chemistry context. So there are two major classes of matter. We will talk about both of these, although in chemistry too you'll talk about one of them more than we will in this class. So the first is mixtures. And these have variable composition. So mixtures are two or more things combined together, as the name implies. We'll give more rigorous definitions for mixtures later on. And really mixtures will be a topic that's more intensely dealt with in chemistry too than it is in this course, but we will see it at times. So there's mixtures, and then what we'll start with, and what a lot of our discussion will be on, are pure substances. And these have constant composition, so you can't vary the composition without changing it into a new substance. And again, more definitions are coming, so this is just kind of to really orient you before we get into these things in more detail. So pure substances have a constant composition. It's one type of matter, and then mixtures are a mixture of two or more different types of matter together. And then each of these has subcategories. So again, mixtures are going to be things that you'll deal with more later on, so we're going to kind of leave this behind after we get through this today. But there are homogeneous and heterogeneous mixtures. You've probably seen this terminology before in other contexts. And a quick rundown of what those mean. Homogeneous means single phase, meaning you can't easily tell that there's two or more things mixed together. So if you have salt water, for example, that's a classic example of a homogeneous mixture. It has salt and water, but you can't just tell by looking at it that it has both of them in it. And then a heterogeneous mixture is one where you have visibly distinguishable parts. So there's two or more things mixed together, and just by looking at it you can tell. So sand is a classic example of a heterogeneous mixture, where if you look at grains of sand, they're not all the same color, they're not all the same size either, but there's a few different things in there that are making up that composition. You can easily tell by looking at it without a whole lot of effort that it's not a single phase substance. But then within pure substances, and this is where we're going to begin and spend a lot of our early part of this course especially, there are two categories here as well. So one is elements, and the other is compounds. So elements are substances that can't be broken down further. So they're the simplest forms of matter. And again, more precise definitions are coming, but essentially it's a type of matter that is as simple as it comes. It cannot be further converted or decomposed anyway into anything else. And then compounds are just combinations of elements. So it's one or more elements mixed together chemically, though. They're not physically mixed together. They actually have chemical interactions between the elements, as we'll define in a lot of detail in this course. So really the whole study of chemistry, not the whole study, but a big part of chemistry is, the way that we can convert elements into compounds and vice versa. How do we combine things to make new substances, and how do we use chemical methods to really use this to our advantage to prepare new substances or to study them and understand them better. So elements and compounds are really the big one for this first part of the course, and we're going to talk about those a lot in the first few chapters. Now, to give you a microscopic view of things, and again, we're not going to really define this carefully now because we're coming to it soon, but if we want to know what the difference between elements and compounds, we can look at things at a microscopic level. So this textbook, as you've seen, is referred to as the atoms first approach, which means that it's it's going from the microscopic level first and then to the macroscopic. There are advantages and disadvantages to that, but I won't get into those. But I want to start by looking at just in sort of the basic view here of what are the differences between elements and compounds and mixtures, and we're going to talk about this as well in a lot of detail. So an element, as we said, is the simplest form of matter. It can't be broken down further. And so if you zoom in, there's only one type of particle, as you will, that makes up an element. So the smallest building block of an element is all the same type of particle. We call those atoms, as you're likely already aware. And that's what an element has. It has one type of atom in it. So and if you break it down even further, sometimes, as we'll see, elements just have single atoms by themselves, or sometimes they have two or more of the same atom attached to each other chemically. So there are variations in this, but the whole point is that an element only has one type of atom. I'm using different colors here to describe the different types of atoms. So either has all red atoms or all blue atoms. Maybe they're connected to each other in some way, but it's only one type in the entire substance. All right. Now, compound is the other type of pure substance, and in this case, we're going to have two or more elements chemically bonded to each other. Bonding is the topic we'll get to, I think, in Chapter 3, so it's coming up a little bit in the future. But anyway, in a compound, you have, in this case, for example, a blue and a pink attached to each other. So it's a compound because it has two different types of elements, or they can be different ratios. They don't have to be 1-to-1. They can be 1 pink and 4 black, so 1-to-4 ratio, or really any whole number ratio of elements can make up a compound. But when it's a pure substance, as we talked about on the last slide, compounds being one type of pure substance, you still only have one type of building block. So in this compound on the left here, every single particle that makes up that compound is one blue and one pink tied to each other, nothing else in there. Same with this one type of particle. We call these molecules, as you're likely aware. It's just one type that makes up a compound, a pure compound. And then a mixture is going to be some combination of those. So you can have a mixture of two elements with each other. So that would be the example here on the left, where it's just single atoms, so each one is an element by itself, but then you mix those two together to make a mixture of the two where they're not interacting with each other, they're physically mixed together. Or you can have a mixture of compounds, as we have over here, where it's two different types of molecules that are mixed together physically but not chemically interacting with each other. Or it could be a mixture of a compound with an element. So really any combination of elements and compounds physically mixed together can create what we call a mixture. And we're going to classify all of these in more detail, so don't worry about the specifics of all of this right now. Really the whole point of this entire course is to take this microscopic picture here and really zoom in and get all the details about it and how these microscopic properties really translate into the macroscopic, what we observe, how we use these materials and all that stuff. And that's really in my mind, the beauty of chemistry is the ability to relate those two to each other, looking at things that are exquisitely tiny that you can't even see with the world's most powerful microscope, but understanding that they're there and understanding how the properties of those little tiny building blocks influence the properties of them when they're all in a huge assembly in a macroscopic level. So really that's the joy of chemistry in my life is really been that link between the two. All right, so let's get into some of the more specifics then of how chemistry started. And we're not going to do a lot with history. There's a small section in the book, and I'm going to try to highlight the important names that you should be familiar with. But really, we want to give you an idea of how did chemistry even start. This course mostly covers things that are fairly old topics. In any introductory course, you're covering concepts and discoveries that have been made usually over 100 years ago or more. But where did chemistry really start before that? So, it wasn't that it was always there. There was some origin of chemistry, some way that it came about. So the first people that really were curious about chemistry were the Greeks, the ancient Greeks, over thousands of years ago, I guess, at least. And they tried to explain chemical changes. So they observed substances changing into other substances. When you burn something, it obviously changes, or sometimes just mixing two things together causes a chemical change. And they were observing with their eyes, things are happening. One substance is changing to another. And they tried to figure out, how this was working, and came up with some proposals. Now, these early chemists, the first two categories here, the Greeks and the alchemists, as we'll talk about, they weren't really using the scientific method. So they came up with some important observations. They actually had some pretty clever ideas that were not terribly incorrect, but they weren't carefully testing those ideas using the scientific method. So that's why we don't really consider this to be real chemistry necessarily, but it's still an important building block for what was to come later on. So the Greeks tried to explain chemical changes, but they didn't really have a rigorous way of testing that. And they proposed 4 fundamental substances. And don't laugh when I write these, because this is true. It's earth, fire, air, and water. Now, I can always tell how much older I'm getting than the students when I mention Captain Planet and see how many of them actually know what I'm talking about. A few of you guys. Captain Planet was earth, fire, wind, water, heart, I think. They didn't propose heart as one of the elements, but they had 4 fundamental substances: earth, fire, air, and water. And in their mind, it was those substances that made up everything. So, and I guess if you think about how things worked at a very primitive level, it kind of makes sense. If you take something from the earth that you dig out of the ground and you mix it with fire, if you burn it, it might change into something else, a different type of earth. So that in their mind, these were the 4 basic things that made up all of matter. Now, clearly this isn't correct, but it was a sort of an early start. And the other really cool thing that the Greeks did, without really any evidence to support it, is they first proposed atoms as fundamental particles. So it took a long time after that to really demonstrate that atoms existed and how to fully characterize them. And I should just get rid of these boxes, they make it hard to fit everything. Anyway, they first proposed atoms as fundamental particles, which was kind of wild because they had no way of really knowing they were there. They just kind of came up with this idea that, all these substances must have these little tiny building blocks, we'll call them atoms. And atoms comes from a Greek word, I don't know if my pronunciation is correct, but atomos, A-T-O-M-O-S, which is a Greek word that I think means building block or small unit or something like that. So they were the first ones to really come up with the idea that there are these small building blocks for everything, but they had no way of really testing that idea, and obviously their proposals for what those substances actually are was quite a bit off. But there's still some very important developments. Now the next ones that came around they persisted for a long time, were the alchemists. Now, we refer to alchemy as a pseudoscience. You may have heard that term in the media before. So, pseudoscience kind of means that, they were trying to do science, but they just kind of had some things wrong, or they didn't really fully understand what they were doing. So they had a goal in mind, and they did experiments, but they had some preconceived notions that kind of got in the way of what they were actually trying to do. They spanned around 2,000 years of our history, so really a long period of time until about the, 1700s or so. Alchemists were around and trying to do their thing, and really their number one goal, and the reason they did all of these experiments that they did, was they were trying to change base metals, or very cheap things like lead, into gold. So at that, in that period of history, and probably not too different than today. Gold was the status symbol. Gold was how you became wealthy and powerful. And so they thought, well, if we could come up with a way to change lead into gold, we're going to basically rule the world. We're going to have all the wealth we could ever want. Not, sort of ignoring things like inflation and supply and demand, all that stuff. But they thought that if they could change metal into gold, they'd be the rulers of the world. And the reason we call it pseudoscience is because we now know that you can't really do that, at least not with the ways that they were trying to do it. I don't think you really can do it at all. But they had this preconceived notion that this should be possible. I just need to figure out how to do it. In reality, it's not possible. So that's why we call it a pseudoscience. They were chasing a goal that was never going to be realized, and they had an agenda behind what they were doing. But they still made some important observations. They did a lot of experiments of mixing different substances together and remarking at the very least on color changes and changes in properties and things that did really form a basis for chemistry, but they weren't really contributing directly to our fundamental knowledge in a very scientific way. Now, getting into when chemistry actually started, the first chemist was Robert Boyle. So, it's kind of, I don't know how you get the label of being the first chemist, but he's really the first one that people recognize as doing real chemistry experiments and kind of birthing the field of chemistry. Now, I'm going to show you some of the pictures of these early scientists. They all look very sour and angry. I don't know why. They made some of the most important discoveries in the world. I'd be pretty happy if I was them. But anyway, this is Boyle. He was one of the first chemists, and what he did, and we'll talk about his discoveries later on in the course, chapter 6, if I'm remembering correctly, when we'll talk about gases. But he did quantitative measurements on gases. And because he was doing things quantitatively, and because he was using the scientific method correctly, he actually learned some important things about gases that we'll talk about. So he was really the first one to do these types of experiments. You might wonder, why did he start with gases? I don't know why he started with that, but a lot of the measurements he was making are pretty simple to make. What's the volume of a gas? How much space does it take up? Or what's the temperature of that gas? What's the pressure? Things that are relatively easy to measure and don't require real sophisticated instrumentation. But he was doing it very carefully and very systematically, so he learned a lot of important things. And he was the first also to propose the concept of elements, these fundamental substances that make up everything. He didn't really have any details about what those elements were or how they combine with each other, but he kind of stated the idea that, well, there might be these fundamental substances that make up everything, and he in large part was correct. And then Joseph Priestley was another very early chemist, and he's credited with discovering oxygen. But really his important contribution, if you kind of take the sum whole of all of it, was that he did careful studies on chemical reactions. So the stuff that Boyle was doing on gases, he was measuring properties of gases and the relationships between those properties, doing sort of very physical studies. But Priestley was the one who's credited with really being the first to do chemical reactions, to really study that process of converting one substance into another, to study it systematically and try to figure out how it works. So these were some of the early ideas, some of the early leaders in the field of chemistry, if you will, that really got the ball rolling in terms of what came to be in the field. Now, what we're going to get into now are from the works of Boyle and Priestley and many other people that will sometimes be named or unnamed. We came up with sort of the three early chemical laws that kind of defined the field of chemistry. And as we talked about a little bit earlier, the very first real slide in this course, I believe, the scientific method, when you apply that scientific method over and over again, what comes out of that are laws and theories. So these laws that we're going to introduce today, starting today and probably finish up next time, we're not going to get through all of them today, these laws are a set of concrete observations that have been proven over and over again to be true and that describe a particular phenomenon, either qualitatively or quantitatively or both. And once we get through these three laws, we're going to then describe the theory that explains all three of those laws together. So very often a theory will explain not just one law, but a collection of laws and really give you some insight into an important physical principle by sort of combining all of them together. So the first law that we'll talk about, which I think is a pretty simple one, is mass conservation. And the person credited with discovering this was Antoine Lavoisier. And so this statement is that in a chemical reaction, the mass of what you start with which we'll in future refer to as reactants, is equal to the mass of what you end up with. So in other words, you're not creating or destroying any mass in a chemical reaction. So the mass of what forms equals the mass of whatever you put into the reaction. And we call whatever forms the products of the reaction. And another way of stating the mass conservation is that matter is neither created nor destroyed. Alright, so this is the law of mass conservation, probably the simplest of the three that we'll get into. And again, Lavoisier, who we just mentioned over here, no, that was Priestley, sorry. But anyway, Lavoisier was sort of the one to come up with this, building off of Priestley's discovery of oxygen. So I think one of the reasons why the law of conservation of mass was sort of not realized for as long as it was, it seems pretty obvious to us, but keep in mind that a lot of the early chemical reactions involve burning things in air. That's one of the simplest reactions you can do with low-tech equipment. And when you burn something, the mass apparently changes, right? But that's because it's combining with oxygen from the air, and people didn't realize that for a while, so they didn't really appreciate that there was actually a conservation of mass. So if you count for the mass of everything that's combining, the substance that you're burning and whatever air, whatever in the air is participating, usually oxygen, those masses will equal each other. It just took a while for people to realize that. Now I have a YouTube video here, but this link is not working, so I'm going to try to queue it up. Alright, let's see. Do I have Chrome? Yes. I don't know if I use Chrome or Firefox for this. What did I just close? Alright, Alright, do I have this? Oh man. Well, I guess I'm still stuck in early semester mode and not come prepared for class. Here we go. Is this it? Yes. Alright, good. Alright, so anyway, here's what we have for the demonstration. Let me just pause this for a second. So he has it's a little bit hard to see here, but he has a liquid on the outside, and then he has a test tube of another liquid on the inside that are currently separated from each other. So what this person is going to do is they are going to measure the mass. So that's 158.2 grams in total. So that's the mass of what they're starting with. So that's listed up here as well. And now he's going to allow the two substances to mix together. This is actually a reaction we will talk about later in the course, and you'll see there's a pretty stark visual change whenever this person stops being dramatic and actually mixes them. Alright, there you go. So there's a very definitive chemical change that happened. We got this yellow, cloudy substance that formed from two colorless liquids. So clearly a chemical reaction happened, but when he puts it back on the scale, the mass is still 158.2. So that's a very simple demonstration of conservation of mass. You can change one thing into another, but the total mass before and after is not going to change. And that's the first chemical law that we'll talk about in this course. And I'll try to pull those videos up ahead of time in the future so I don't waste time finding them. Alright, so back at it. So that's the demonstration of mass conservation. That's our first chemical law we'll talk about. Not a whole lot more to say about that. Let's get into the next one, which is definite composition. So definite composition deals with the composition of a compound. So remember, a compound is a mixture of two or more elements now. I guess it technically applies for elements as well, but the composition of an element is always 100% that element, so it's not really very useful to describe for that context. But it's for compounds specifically, and this was discovered by Joseph Proust, another early chemist. And so the way that this works is that if you have a given compound, again, compound has two or more elements, it's always going to contain the same proportion of those elements. And that's regardless of the source that we get it from. Okay? So there's a concept that then comes out of this, a little bit more quantitative or mathematical concept, which is the idea of mass percent. So to get into this, let's say we have carbon dioxide. We all know that we breathe that out when we're respirating. So let's say we have 44 grams of carbon dioxide. That would actually be a lot, but as we'll learn later on, that's going to be about 22 liters at room temperature, or slightly less than that. Anyway, if you have 44 grams of carbon dioxide, the two elements that make up carbon dioxide, as you might already be familiar with, are carbon and oxygen. And that 44 grams will include 12 grams of carbon, and 32 grams of oxygen. Now this statement here, which is true and is just a random example that I picked, kind of demonstrates both of those mass laws in one. So if you're going to make 44 grams of carbon dioxide, you have to combine 12 grams of carbon and 32 grams of oxygen. 12 plus 32 is 44. That's conservation of mass. So the amount of elements that you combine equals the amount of compound you make. But then what the law of definite composition says beyond that is if you have 44 grams of carbon dioxide, it will contain exactly 12 grams of carbon and exactly 32 grams of oxygen. It can't have another ratio of those two and still be carbon dioxide. So if the ratio was different, it would be a different substance altogether. So and it's regardless of source. So whether we're talking about 44 grams of carbon dioxide that you guys breathe out as your hearts are racing trying to learn all this chemistry, or whether we're talking about 44 grams of carbon dioxide that bubbles out of the ocean from the ocean floor, and we collect the same, that's always going to have the same ratio of carbon and oxygen no matter where we get it from, or if it's carbon dioxide that we form by burning something in a fire. So really, no matter where we get carbon dioxide from, if we have 44 grams, it's going to have 12 grams of carbon, 32 grams of oxygen, that exact amount. Now that said, it's not very convenient to just always talk about these random amounts of substances. Why did I pick 44 instead of some other number? So really the way we define this is in terms of mass percent, which is then scalable to any amount of substance that you have. So the mass percent is just the mass of whatever element you're talking about. So mass percent is going to be defined for each element in a compound, whether it's 2 or more than 2. So it's going to be the mass of element X, whatever X is that you're interested in, divided by the total mass of compound. Now something we will see over and over again in this course is that whenever you see percent, you have to take the ratio and multiply by 100, so don't forget that. And this ratio, mass of the element divided by the mass of compound, is often referred to as mass fraction. And so if you multiply the mass fraction by 100, you convert it into a percent. You might see the term mass fraction once in a while in homework assignments. Mass percent is probably more common, but they both mean the same thing. It's just whether it's expressed as a percentage or as a ratio between 0 and 1. Okay, so that's the mass percent in its sort of generic definition. So if we want to look at carbon dioxide, then the mass percent for oxygen we just take the numbers that we have. So we have 32 grams of oxygen. We have 44 grams of carbon dioxide. So that's mass of element, 32 grams, divided by the mass of the compound, which is 44. We multiply by 100. And so we get 73% by mass oxygen in carbon dioxide. And that's a more convenient number to use because no matter how much carbon dioxide you have, you're going to have 73% oxygen by mass. And you can scale that to any amount of CO2 you have. We'll see later on how we use this as sort of a conversion factor. And then finally, if we want to do the other element, which is carbon. So as I said, we can define mass percents for any of the elements in the compound. We have 12 grams of carbon, 44 grams of CO2. We also multiply that by 100, so we get 27% for carbon. So for whatever element we want, we can take the mass of the element divided by the total mass of compound, multiply it by 100, and that gives us mass percent. Now, you should notice then that these two add up to be 100%. So whenever you have the mass percents of all the elements in the compound, in this case there's only two of them, the sum of them will be 100, and that's an important relationship we'll need to remember sometimes later on. So the sum of all the mass percents will equal 100, of course, and this is how we find the individual ones. Okay, so let's do a quick sample problem then that's related to the law of definite composition. So you may have seen this before. Pyrite, which is also known as fool's gold, it's a compound that just consists of iron and sulfur, which are two things that are actually dirt cheap, so it's not anywhere close to as valuable as gold. And if we have a 50-gram sample of pyrite, it contains 26.7 grams of sulfur. Now the question is asking, what is the mass percent of iron in pyrite? Now one thing I'm going to emphasize throughout this course are problem-solving strategies. This is a problem-based course, and most of the problems are word problems of this type. So what I like to do whenever I'm setting up a problem, this one's not terribly complicated. They will get more and more complex and have more and more data and information given to you as part of the problem. I like to go to the very last sentence first because that typically tells you what the question is asking. And sometimes, the information is either not all important that they give you, or some pieces of information are more important than others. And so if you go to the very end of the question, you can sometimes tell what do I need to solve this problem a lot quicker. So we're looking for mass percent of iron in pyrite. So as we recall, the definition of mass percent, we're looking for iron in this case, is the mass of iron, the mass of that element, divided by the mass of the compound, in this case pyrite, times 100. And so we just need to find these two numbers and put them in. Now the number that's given directly to us is in the problem, mass of pyrite. We're told that we have exactly 50-gram samples. We already know the denominator of this relationship. We have 50 grams of pyrite in this sample. But we need to figure out how much iron is there, and that's not given to us directly in the problem. The problem instead gives us the mass of sulfur. So keeping track of what we have and what we need, the mass of pyrite is given to us as 50 grams. Then we remember from the law of conservation of mass that if we have two elements combined to make a compound, the sum of those two has to equal the mass of the compound. So we don't have the mass of iron directly, but we know that if we have the mass of the two together, that has to equal that total mass of compound, which is 50 grams. And so therefore, if we want the mass of iron, these three little dots in the triangle means therefore. If you're not familiar with that notation, I'll use it a lot. Anyway, the mass of iron is the mass of the compound we have, which is 50 grams, minus the mass of sulfur, and the rest of that must be the iron that's in there. So that comes out to 23.3 grams. So in other words, we didn't directly give you the mass of iron in this case, but using the law of conservation of mass, we know that if 26.7 out of our 50 grams is sulfur, the rest must be iron. So that's the number we're going to put up here for the mass of iron. Then we multiply by 100 to convert it to a percent, and we should get 46.6%. Now there are other ways to do this problem as well. We could have first found the mass percent of iron and then subtracted it from 100. That would give us the same number, so there are some variations on how I did this. But the way I always like to set things up, if possible, is use the basic definitions that we know, go to what the question is asking and sort of write that out, and then figure out what information do I need to get to that final answer. Alright, so that's an example of a definite composition sample problem, and calculating mass percents and using them in different ways is going to be a big part of what we do in that part of the course. Now the last one I'll give you is a little bit more complicated. So it's the same situation here. We're telling you about pyrite. We also give you the same given information. 50-gram sample contains 26.7 grams. But this time we want to ask how many grams of sulfur are in a 1.235 gram sample of pyrite. So as I said, mass percents, they apply to any amount of compound that we have. And so if we have only 1.235 grams instead, how much sulfur is in there as opposed to the entire 50 grams that I gave you? So we're going to, essentially in this case, we're going to use the mass ratio or the mass percent as a conversion factor. So there's a couple ways we can do this. Since we have the answer from the first part, what we can say then is that the grams of sulfur, which is what we're looking for. So again, when I set up problems, I write down what I'm looking for, which is the mass of sulfur. And then I start with what I'm given, which is we have 1.235 grams of pyrite. So we want to figure out how much sulfur is in there. And we're going to use mass percent, or mass ratio in this case, as it may be, as a conversion factor to relate how much sulfur is going to be in this amount of pyrite. So we can use the result from the last problem, or we can just use the raw data that we're given, 26.7 grams and 50. There's, again, more than one way to do this problem. But if we use the result from the last problem, we saw that in the last problem we found that pyrite has 46.6% iron, and the rest would be sulfur. So we either have to figure out the mass percent of sulfur, or we have to use the numbers here. So the mass percent for sulfur is and we set up here for iron is 46.6, so the rest of that has to be sulfur. Please tell me I did that math right. I'm doing it in my head. Okay. 53.4% is the mass percent of sulfur. And we can use mass percents as conversion factors between one substance and another. So if we have 1.235 grams of pyrite, we can use this percentage as a ratio. So 53.4% by mass sulfur means that in 100 grams of pyrite, we have 53.4 grams of sulfur. All right, that's what that 53.4% means out of 100. So 100 grams of pyrite would have 53.4 grams of sulfur. That's what mass percent tells us. And we want to write it in this way because we want units to cancel out, so that grams of pyrite cancels out, and we convert into grams of sulfur, which is what we're looking for. Okay? So that's how we know to write the ratio in that way. And so when we multiply it out, we get 0.659 grams of sulfur. And I think I should have had one more significant figure. I hope you'll forgive me if we assume that mass percent is an absolute quantity. So that's going to be choice A in the multiple choice. The other way we could have done this is, instead of using the percentage, we could have just used the raw numbers, 26.7 grams of sulfur over 50 grams of pyrite. So this introduces the important concept then that mass ratios can be used as conversion factors. And that's going to be another type of problem you'll see over and over again on the homework assignments, is using these mass ratios or mass percents to convert from amounts of one substance into amounts of another. So we're going to learn more sophisticated ways of doing that later in the course, but for now we have these mass ratios as kind of the way we do it. It's one of the more primitive ways of defining composition. So the way we can use these then is, if we know the mass of element A, we can relate that to the mass of another element in the compound, let's call it B. And those can be related also to the mass of the compound. And this all comes from that mass percent information about the relative composition of a compound in terms of each element that makes it up. So we'll see probably more examples of this later on. You'll see a lot in the first homework assignment. But I think that wraps us up for today, and I'll see you guys on Wednesday.